We will now review the concept of scientific notation and look at several examples. Let's begin with a definition. A number is in scientific notation when it is written in the form a times 10 to the n, where 1 is less than or equal to the absolute value of a, which is less than 10, and n is an integer. So let's just write out a few examples of scientific notation so that we can see the format that we'll be working with. So let's choose an a value and an n value. Our stipulation on the a is that the absolute value of the a has to fall between 1 and 10. So I'm simply going to select a number between 1 and 10. I'm going to select 4.2. And I'm going to follow this format. So times 10. And I'm going to select an integer for the n value. So maybe 5. And so what I have written is one example of what scientific notation looks like. Let's do one more. Again, I'm going to pick an a value in between 1 and 10. What if I pick negative 3.7 for the a? Would that work? And it will, because our stipulation says that the absolute value of the number has to be between 1 and 10. So the absolute value of negative 3.7 would be positive 3.7, which does lie between 1 and 10. Following the rest of our format, times 10, and we're going to raise it to an integer. I could choose negative 3. So you want to remember that integers can be positive or negative numbers. Let's look at another example. The distance from Earth to the Sun is approximately 93 million miles. The scientific notation is 9.3 times 10 to the 7th. I just want us to look just for a second at how these two numbers are equivalent. So let's take our scientific notation, 9.3 times 10 to the 7th, and let's discuss what this means. When we multiply by a factor of 10, 10 to the 7th, if this number, our exponent, is positive, then we're going to be moving our decimal place to the right. If the number had been negative, we would be moving our decimal place to the left. And the number tells me how many places to move. So here's what's going to happen. If I write down the 9.3, then what I want to do is I want to move that decimal place 7 places to the right. So I'm going to move it over. That's 1 place, 2, 3, 4, 5, 6, 7. And in these spots that I left, I'm going to put some zeros to kind of hold those places. And so the number that we have here is 93 million. And so now we can see that 93 million is equivalent to 9.3 times 10 to the 7th in scientific notation. Let's try another one. The mass of an electron in kilograms is approximately, and we have a number with 0.0, many zeros, and then 911. Now, the slide says that clearly this is not a convenient number to work with. And so we want to write it in scientific notation instead. So let's look at how many places we're going to have to move our decimal in order to produce this big, long decimal number that we have. So remember that the a value you choose has to be between 1 and 10. So when I'm looking at my number here, the 911, I am going to put it as 9.11 for my a value. That is a number between 1 and 10. Now, how do we get from 9.11 to this decimal? We're going to have to move the decimal place back to the left. So I know that my exponent on the 10 is going to be a negative number. Now, what I need to do is figure out how many places I need to move it. So let's count. If my decimal is here between the 9 and the 1, let's count back and see how many decimal places we need to move. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and 31. And so our decimal would be equivalent to 9.11 times 10 to the negative 31 power. Our third example says the speed of light in a vacuum is approximately 3 times 10 to the 8th meters per second. In standard notation, this number is written as, and so let's do that. Let's figure out what this number is out of scientific notation. So remember that the fact that this is a positive exponent means we're going to move to the right. So we're going to write our number down, and the decimal place right now sits right beside the 3, and we're going to move 8 places to the right. So 1, 2, 3, 4, 5, 6, 7, 8, and we're going to add zeros in each of these spots. And so our number in non-scientific notation would be 300 million. We can also use scientific notation to help us simplify expressions. So we're going to look at 2 examples here. The first example says, in parentheses, 3.6 times 10 to the negative 12 times, and in parentheses, negative 6 times 10 to the 4th, and that makes up the numerator of our fraction. And for the denominator, we have 1.8 times 10 to the negative 6. And we want to simplify this. The easiest approach to use is to treat your a values separately from your powers of 10. So I'm going to go ahead and simply write down the a parts to each of these expressions. So 3.6 times negative 6 on the top and 1.8 in the denominator. And then we're going to work on the power of 10 that we need. So let's remember our laws of exponents, and let's look at what we have here. We have a 10 to the negative 12th, a 10 to the 4th on the top, and a 10 to the negative 6 on the bottom. So let's look at combining these exponents. Well, we know that we have already said that it's often easier to deal with positive exponents than negatives. So I'm going to first rewrite this with positive exponents, which means that this 10 to the negative 12 will need to come down to the denominator. The 10 to the 4th can stay. And the 10 to the negative 6 that's currently in the denominator, I'm going to pull it to the top, making it 10 to the 6th. Now, for the numerator, we know 10 to the 4th times 10 to the 6th. If the bases are alike, our rule is to add the exponents. So we're going to have 10 to the 6 plus 4 makes 10th over 10 to the 12th. Our rule for exponents here, when we have a fraction, tells us that we need to subtract. So we're going to have 10 to the 10th power minus the 12th power, which would equal 10 to the negative 2. So coming back up into our problem, we know that our power on the 10 is going to be a -2. So now what I'm going to do is I'm going to do my multiplication on my calculator, 3.6 times -6. I'm then going to divide that by 1.8, which gives me -12. And I'm going to leave it times 10 to the -2. So that is my answer in scientific notation. It says that we can write it in scientific or standard notation. And so let's do it both ways. If we have -12 times 10 to the -2, remember that this -2 tells you to move your decimal place 2 places to the left. So if my decimal place is currently after the 2, we're going to move it back to the left 2 places. And so our answer would look like 0.12, and that would be negative. So that is our other option for our answer. All right, let's try this one more time. So we have one more problem to look at here. Again, we're going to separate the numbers, so the A parts, from the powers of 10. So our problem reads 7 times 10 to the 34th times 3 times 10 to the -12, that's the numerator, and the denominator will be 6 times 10 to the -7. So I'm going to go ahead and do the 7, the 3, and the 6. So 7 times 3 gives me 21. We'll divide by 6. And so we know that our number will be 3.5. Now let's deal with the power of 10. So again, I'm going to separate this, and I'm going to say I have 10 to the 34th on the top. I also have 10 to the -12 on the top. And I have 10 to the -7 on the bottom. We'll work this out by making positive exponents first. So I'm going to leave the 10 to the 34th in the numerator. I'm going to take the 10 to the -12th to the denominator, making it positive. And the 10 to the -7, I'm going to move up to the numerator, making it positive. Our bases here are alike, so we're going to add those exponents. So 34 plus 7 is going to give me 41. And we have a 10 to the 12th in the denominator. 41 minus 12 is going to be 29. So we have 10 to the 29th. And so our final answer in scientific notation will be 3.5 times 10 to the 29th. Now, it wouldn't be practical to write this in non-scientific notation because we would have to move our decimal place 29 places to the right. And so we'll simply leave this in scientific notation.